Let us now start deriving our kinematic equations. I'll start by drawing our reference frames. I'll also now put a local reference frame attached to our WMR. And let's add a horizontal line that'll help us indicate the rotation angle, going from X in the G frame to X in the R frame. And we'll call that angle theta. To help us understand the equations we're deriving, we'll occasionally want to look at what happens when theta equals 0 degrees. And 45 and 90 degrees. Those are going to be nice touchstones for us to keep coming back to as we're trying to understand the directions and the signs that we'll have in our equations. I also want to take a moment here to point out a couple of physical quantities that we'll need. Let's define the origin of our WMR, of its local coordinate frame, right here in the center of the two axes of the axles. So that center point there. We'll also define the distance between the wheels by d, and the radius of each wheel as r. What we want to have equations for eventually is the change in the global coordinate frame's x value. And I'll put a dot there to denote it's the derivative. That's just shorthand notation for saying d dt of x. So I'll favor using this dot notation just for simplicity. So we want to know what this equation is equal to. Likewise, how y changes in the global coordinate frame. That's analogous to looking at our robot here and figuring out if it's moving purely in the x-coordinate, in the y-coordinate, or some combination of the two. And let's look at why I'm so focused on the change, so x dot and y dot, instead of just looking at x and y themselves. Well, if we consider this equation, we'd want to know what's on the right-hand side, and maybe terms that we would be looking at would include x in the r frame, maybe theta, maybe y in the r frame. But none of these actually have an impact on our value of x in the global coordinate frame. In fact, let's take a quick second here to figure out what x in the r frame and y in the r frame might be. Pause the video here and take a few seconds to see if you can come up with an equation for xr and yr. These are actually both equal to 0. And that's because we have fixed our R frame to the chassis itself. So back over on this picture, this point here, it moves around with the robot itself. So the robot is always defined at xr equals 0 and yr equals 0. It's just not a useful quantity for us to look at. And it doesn't tell us anything about x in the g frame. What we really need for this equation is to just know what the transformation to G from R is. And as a reminder, that's some combination of a rotation and a point. Here's a good time to mention exactly what these two quantities are. Well, to begin with, we need to know what they are. Later on in the semester, when we're talking about localization, we won't necessarily know what they are. But to begin with, when we're doing pose estimation, we actually have to know the original values for those. So that would be akin to saying we know what the rotation at time step 0 is. And we know what the position at time step 0 is. And then we could move forward through time and know what the position at time step 1 is and the rotation at time step 1. All the way to the position at time step t and the rotation at time step t. But that's exactly what we're trying to get to, is how do we compute these values? How do we go from the initial rotation and position to the one at time step 1? And for that, we need to know how these two quantities change over time. So for that reason, we're really not all that interested in this equation here. Instead, what we care about are the equations that are at the bottom. And I'll break it down even more simply here. We'll first look at what happens when we translate along the xr axis. And then separately, we'll look at what happens if we translate along the yr axis. And so we'll need those contributions to x dot. So for x dot, we'll first look at what happens as we translate along x. And so we want to figure out this relationship. Clearly, these are not equal. So they're not strictly equal. So for example, if I take the current robot's orientation and translate it in the positive xr direction, you can see that doesn't perfectly translate to moving along the xg direction. It would actually if theta were equal to 0. So if I take this and rotate it so that the xr and xg line up, then these two quantities actually are equal. But for the more general case, we want to figure out what happens when we translate in the xr. How does that impact x dot in the global coordinate frame? And that's where looking at these three special cases is going to be helpful. So if both xg and xr are in the same direction, we really want to just be multiplying this by 1. When they are 90 degrees apart, so that would be if the robot was facing straight up, it would be moving along this axis, which means we have no translation along this axis. So when they're 90 degrees apart, we'd really want to multiply this by 0. And probably not surprisingly, but at 45 degrees apart, it would be something in between. In fact, that relationship is given by the angle here, theta. So what trigonometric equation or function maps to having a 1 when theta is 0, a 0 when theta is 90, and something in the middle? It's probably not too much of a shock that this relationship is determined by the cosine of theta. Likewise, we want to know what happens when we translate along this positive yr direction. So what happens to x dot in the global coordinate frame if we had a pure translation in the y dot in the r frame? this would be a good time to pause the video and see if you can map it to the test examples we have here. Well, if our robot is rotated at 0 degrees, like so, our x direction is in the opposite. So we would need a negative sign over here. So that would be something like -1 in the case of, and that's wrong, in the case of 90 degrees. And when theta is 0, that means Ry is pointed straight along the y-axis, the global y-axis, we would have 0. And so this relationship is going to be given by negative sine of theta. So with those two components, we can now list out what x dot in the global frame is. And it'll take contributions from both translation along xr and yr. And we should do the same exercise for figuring out what happens to y in those two cases. So for this first one, it's what happens if we have some translation along x dot, and then the second one in y dot. So the way to map the two sides of the equation is this x here maps to this x, and this y maps to this y. Likewise here. Again, referring back to our examples here, if theta is 0, meaning the robot is pointed directly along the global x frame, then y dot is 0. So that would correspond to sine of theta. And if theta is 90 degrees, that means that the robot would be driving straight along the y-coordinate, which means there's no contribution to the x-coordinate. So that checks out for sine as well. Looking at our second contribution here, I'd encourage you to plug in numbers for theta equals 0, 45, and 90 to see if you can come up with y dot r cosine of theta. And so this gives us now our two equations of motion in the x and y global frame coordinates. And these are two important equations that we'll need to remember for the rest of this chapter and in future chapters. But our robot doesn't just move along in these two directions, or along its local directions. It also rotates. So we need to have a final equation here for theta dot in the global frame. And you can picture we could actually scoot this robot along these two directions without actually rotating it at all. So there's no contribution from either x dot or y dot in the r frame. You can also picture rotating our robot at any point in space, even at the origin. And at all points in space, our relationship between the change in angle and the global frame is that it's equivalent to a change in angle in the local frame. So those quantities are strictly equal to each other. And so for the remaining of the slides, I'll just refer to that as theta dot. There's no distinction between the two. A good way to visualize that, if it's not something that sits well with you, is if I have a rotation of an object here, maybe I then rotate it (45°). That's equivalent to if I had the same object anywhere else in space and had rotated at that 45°. And the case of having it at different translations, it's really just those translations that are different. The rotations themselves are the same. So these three equations are going to do a lot of work for us. However, they're not even the most basic equations that we need to derive for this chapter. We still don't actually know what causes a translation in x dot or in the y dot directions. We don't have direct control over that. When you're writing code for your robot, you are not going to be able to say, hey wheels, translate in the XR direction. Instead, you're going to send PWM duty cycle signals to the motor driver, and it's going to independently apply a torque to each wheel. So that's really what our control signals are. We really just have control over two quantities. And I'll call those phi right and phi left. And those are going to be the angles of deflection for the two wheels. And I don't know if you've ever considered this. I don't know how much you actually care about what the current rotation of the wheel is from the first time that you ever attached your wheel to the robot. Your axle actually is a d-axle, meaning it looks something like this. So we could actually measure and know the angle of deflection for the two axles at any given point in time. We're just not going to find that information very useful. If your robot's at x coordinate and y coordinate 5, -2, you don't really care what the angle of the wheels are. Any angle of the wheels is really going to be the same to us. They don't behave differently at different deflections. What I'm getting at here is we don't really actually care about controlling the angles. Again, what we really care about are changing the angle, the changes to angles over time, or rather the angular velocity of your wheels. So that's what we're actually directly controlling, is the angular velocity of the wheels. And what we now need to figure out is how does that relate to x dot r, y dot r, and theta dot. So we want some equations that are dependent upon these two quantities and any geometry that we need to take into account. So let me drag some of that over from the previous slide. It'll be useful for us to think about what actually happens when we apply an angular velocity to the two wheels. So what happens when we do that to x dot? Well, if we apply an angular velocity to this wheel and nothing to the other, the robot will trace out an arc and sort of pivot around that other wheel. So likewise, if we fix the right wheel, we'll pivot around that right wheel and rotate in the opposite direction. Another useful scenario to think about is what happens if one wheel goes backwards and one wheel goes forward. So for each phi, for each motor, we'll have values of 0 for both, and the impact on x dot, y dot, and theta dot are that if both motors aren't moving, then nothing is happening to those quantities. If both are positive, and let's say they're positive and equal, we'll have a positive translation in x. Nothing will happen in y. So in this scenario, both motors are moving forward, so we're not moving in the y direction at all. And theta is also likewise 0, where there's no rotation. If both are negative, then we'll have a negative direction for xr, so we'll be moving backwards. And again, nothing will happen in y or theta. I cleaned up this slide just a little bit so I could show all the different cases that are worth considering. So for each of the two wheels, I also swapped the sides so that left was on the left. So for the two wheels, they could either be stationary, given a positive acceleration, or negative. So I'm saying positive in the forward direction and negative in the reverse direction for both wheels. You can see from the table that there are a couple of ways that we can affect just one of these quantities. So we can impact just the x-coordinate if we set both motors to positive or both motors to negative. In both cases, we get a pure translation in x. So it makes sense that if both of these quantities are the same, we'll only impact this, and it won't impact either the rotation or the y-coordinate. The exact relationship also depends on the radius of the wheel. You can imagine if you're spinning an extremely large wheel at the same rate as a small wheel, you'll travel much further on the large wheel. In fact, that equation is given by, so I'm going to define two new quantities here. It's going to be the velocity at each of these points, so we'll call this VL, and the velocity of this point, VR. VL is equal to phi left dot times the radius of the wheel. And similarly for the right wheel. Two useful cases to look at here are the case where both are positive and the case where they're opposite. So let me focus in on those two rows. If both values are positive, we have positive translation. If one is positive and one is negative, we have zero translation. So it's probably not too much of a stretch to say that the relationship looks something like this. And I'll give you a chance to, or I'd like you to take a chance to pause the video and see if you can make this equation fit with those two rows that I have highlighted below. The way that I like to think about this equation is that the forward velocity is really just the average of the velocity of those 2 points. And for reasons that will become clear pretty quickly here, I'm going to swap the order of those two. It's not going to change this equation since they were just added together anyway. But I'll put right and left. From the table, you'll also notice that if we zoom in on the y column, the y dot with respect to the r reference frame column, any time that you have a change in r, it's accompanied with a change in one of the other parameters as well. Just highlighting each of those rows. The upshot here is we actually have no way of directly controlling y dot. And that should make some sense, because we have no way to force the robot purely along the y-axis. So y dot actually is always just 0. We can certainly change the value of yg dot in the global frame, but we already know you can't change the value of y in r. That's always equal to 0, just like x in r is always equal to 0. Those are fixed to the frame. Here we're now also learning that we have no direct way to control translation along the local coordinate y-axis. Instead, if we want to be turning, we have to be moving forward at some rate, and then also rotating. And for rotating, there is another relevant diagram that I'll try to squeeze in here into this space. Give myself some space to draw in. Imagine our robot is sitting like this with its two wheels, and just one wheel is rotating. Let's say it's the right wheel. So in that case, we would say VL is equal to 0, and VR is equal to, let's just say, 1 radians per second. 1 radian per second. What happens is we pivot around this point and trace out an arc. That arc defines a change in theta. Or more correctly, they're similar triangles, so that picture works, but more correctly, the change in theta would be measured from here. That arc length, given by this arc, can be determined by using the arc length equation, which would be theta multiplied by, normally you would use r for the radius of the arc, but in this case we have a better descriptor of what that distance is from this point to the other point as it's traced out. That distance is d. So theta times d is that arc length. And that is going to be equal to the distance traveled by the robot according to the wheel's radius and the angle of deflection of the wheel. So that is equal to phi times r. So solving this for theta, we would get that theta is equal to phi r divided by d. But just like we don't really care about the exact value of phi, we don't really care about the exact value of theta. What we really care about is the change in both of those. So we can take the derivative of both sides, and that says that theta dot is equal to phi dot r divided by d. So that equation tells us that over here, phi, and that was for the right side, times r over d is going to be one component of that equation. If you were to flip this picture around and say you were fixed on this side and tracing out an arc on the other side, you actually get a negative angle. And this is why I swapped the two right and left above, is because typically it's nicer to say phi right subtract phi left. And for a little bit more symmetry, since these are both divided by d, we can group them together. And that's a good place to wrap this rather long video. In the next one, we'll talk more about how these equations can be grouped together into a proper kinematic model.